All right, good afternoon, and welcome to our 4 o'clock briefing today, the search for extraterrestrial life with new generation technology. We have 3 speakers on our briefing today. They are Jill Tarter, Chair Emeritus for the Seti Research at the Seti Institute in Mountain View, California; Andrew Siemion, Director of the Berkeley Seti Research Center and Lead Investigator of Breakthrough Listen at the University of California, Berkeley; and the Bernard M. Oliver Chair for Seti at the Seti Institute; and Victoria Meadows, Professor of Astronomy at the University of Washington, where she's also the Director of the Astrobiology Program. So we will hear short remarks from each of our speakers, and then we will open it up to Q&A. Thank you.
Okay.
Oh, we're doing you.
Go ahead, Vicki.
No, we're doing you first because you have the slides.
All right. Okay. I don't know what the rest of you are doing in 2016, but I know that year I spent a lot of time talking with some of you trying to explain why the discovery of extraterrestrial civilization and technology had not been verified. So no, aliens weren't building megastructures and dimming Boyajian star. A thin disk of dust is a better explanation. And no, alien civilizations around 234 stars were not sending very short optical pulses of exactly the same duration. A processing artifact due to the non-random spacing of absorption lines in stellar spectra is a better explanation. And no, a high-frequency radio signal detected only once at the Rattan 600 was not being sent by aliens. Russian military satellite is a better explanation. The media, the public, and the SETI community need a good metric that will convey both the significance and the credibility of a claimed detection. Something as simple as the Richter scale. So in 2001, we developed the Rio scale from 0 to 10 for this purpose. It was subsequently modified, but it didn't get much traction, and it didn't adapt itself well to the 24/7 news cycle of today. So last year, Duncan Forgan, led an effort with a team to rebuild the scale. It's now called Rio 2.0, and members of a discovery team can use a web-based calculator on Duncan's site to quickly estimate the significance of the detection as well as the potential for it being an instrumental problem, interference, or a hoax. So next time you're called upon to report an ET discovery, please ask for the Rio score, and you can calculate it yourself. So this continues to be a work in progress, and the community has not formally endorsed it, so we'll keep working on it. Finally, there are some new and near future optical SETI projects that are being built specifically to inspire confidence in the detection of any signals that they may make. The Veritas OSETI observing project uses 4 existing 12-meter gamma-ray telescopes at the Whipple Observatory in Arizona, plus newly created software to co-observe flashes coming from the same sky pixel. Dedicated observations allotted 30 hours per year will concentrate on the breakthrough listen targets, and archival data will be reanalyzed. NanoSETI is being built by Shelley Wright and her team at UC San Diego. And they're planning to mount 100 Fresnel lenses on a geodesic dome of a new observatory and focus them on multi-pixel photon counters in order to observe about 10,000 square degrees of the sky for optical pulses lasting 1 nanosecond to a second. The first 2 Fresnel units have been installed in the dome of the Lick Observatory astrograph and are now undergoing engineering tests. And lastly, Laser SETI, being built by Elliott Gillum, based at the SETI Institute, will use wide-angle astronomical grade cameras and transmission gratings to look for bright optical laser pulses lasting between a nanosecond and a minute. To achieve all sky, all the time coverage will require 15 sites globally. Each site will have 4 enclosures. Each enclosure will contain a pair of cameras. Each site observes all the sky above 15 degrees from the horizon, and the sites are paired to co-observe. The first two enclosures have been undergoing engineering tests from the roof of the Robert Ferguson Observatory in Northern California since August. And the next two enclosures will be installed at the Haleakala Observatory in Hawaii. Installing two half observatories will be the quickest way to validate the very low false positive rate expected. So neither PanoSETI nor Laser SETI are yet fully funded, so we cannot say when they might be completed. But both have the potential to detect as yet unobserved optical counterparts of astronomical phenomena. I'm sorry, I ran over by a minute.
No, that's great. Thanks, Andrew.
Sure. Well, maybe I'll take a bit of a step back. Our session tomorrow, I think, is really exemplary of a sea change that we're seeing in astrophysics and astrobiology, and that is a recognition, I think, unlike there has ever been in this field, of the possibility for life beyond the Earth, and the ways in which we might try to detect that life beyond the Earth. There are three methods that we can use to do that, and from Vicki, I think you'll hear about two of them: in situ investigations of bodies in our own solar system and exploration of exoplanet atmospheres. But there's a third, which is near and dear to my heart and to Jill's heart, and other people in this room, which is to look for technologically capable life, to look for artifacts of the technology that might be created by very advanced civilizations. And the advantage that this method has over perhaps the other methods is the tremendous range that we can search for these kinds of emission. We could detect a radio transmitter equivalent in power to the most luminous radio transmitter that we have here on this planet from across the galaxy with some favorable assumptions. And that's truly an amazing realization. So even though intelligent life, technologically capable life, might be much more rare than basic life, we have reason to believe that might be true. We can detect it at a tremendous range, over tens of billions of targets just in our own Milky Way galaxy. I think we owe this sea change really to two things, in particular in the search for intelligent life, which is the Kepler mission, the discovery of the ubiquity of extrasolar planets, the fact that essentially all the stars in our galaxy have planetary systems, and the rather dramatic infusion of private funding into the field of SETI over the last 5 years. In 2015, at the Royal Society, at a press conference not particularly unlike this one, the Breakthrough Listen program was announced, a 10-year, $100 million effort to conduct the most comprehensive, sensitive, and intensive search for extraterrestrial intelligence in history, a search that now counts some dozen observatories as part of that program. So tomorrow we'll announce two new results from the Breakthrough Listen program. The first is the second Breakthrough Listen data release. It's the largest release of publicly available data for the search for extraterrestrial intelligence in history, nearly 2 petabytes. It contains the first observations of the galactic plane using the Parkes telescope, the first observations of the galactic center using the Green Bank telescope, and a number of other targets as well. We'll also be announcing our latest science results that were led by Sophia Sheikh, a graduate student at Penn State. She's here in the audience, and I certainly encourage you to chat with her about her work. She led a survey of a region of the sky called the Earth Transit Zone. This is the part of the sky where other stars, with presumably civilizations around them, could see our Earth transit in front of our sun, and thereby might recognize that there were an intelligent civilization on our planet and might target us for a beacon transmission. We're also going to be announcing tomorrow with the SETI Institute a partnership with the National Radio Astronomy Observatory to bring SETI in a very significant way to the most productive, well-known centimeter wave radio telescope in the world, the Very Large Array in New Mexico. Many of you may know this telescope from the movie Contact and its rather pivotal role that it played in that movie. Those of us in the astronomy community know it as truly, as I said, the most productive and capable centimeter wavelength radio telescope in the world. And we're incredibly excited to partner with the NRAO to bring a world-class state-of-the-art SETI program to that facility. Thanks.
Okay. All right. So I'm Victoria Meadows. So tomorrow I'm going to be talking about essentially at the astrobiological search for life in the universe. So not focusing so much on the type of organisms that can develop telescopes and technology, but just looking at sort of a more fundamental look at how microbes actually impact the environment and produce changes in a planet's environment that are detectable over parsecs. So basically, my main message is that after millennia of wondering whether Earth is the only inhabited planet, even for primitive forms of life, we stand on the brink of being able to study terrestrial planets orbiting nearby stars now. So we have within our scientific and technological grasp the ability to start that search. We have promising targets for observation already identified, and the James Webb Space Telescope, which will launch in 2021, and also extremely large telescopes that are being built on the ground here. We'll see first light sometime in the mid-2020s. Will have the instrumentation and the capabilities needed to confirm the presence and nature of atmospheres on small Earth-sized planets orbiting around other stars. So this capability will allow us to search for signs of habitability and life in those atmospheres as well. So my NASA-funded research team, which is called the Virtual Planetary Laboratory, has spent close to a couple of decades now trying to figure out what types of signs of life might be detectable to these sorts of telescopes, and also trying to understand how we would actually interpret those signs of life should we detect them. And part of that is trying to understand false positives, so that would be processes within a planetary environment that actually mimic the thing that we think we're looking for, that we think is due to life. So the research from my group has recently shown that the James Webb Space Telescope is probably going to be unlikely to be sensitive to oxygen coming from a photosynthetic biosphere on a planet, but it may show stronger features from oxygen that are due to the loss of the previous loss of an ocean from that planet. So that's a potential false positive for oxygen in an atmosphere, but we've shown that we can potentially discriminate between those two types of things. We do believe, though, that we are likely, if they are present, to see signatures from carbon dioxide and methane in an exoplanet atmosphere. And if they are present and we detect them, that is potentially a sign of life from a biosphere that's very much like the one that was present on our early Earth. And so there's a potential to, if we see planets at different stages of evolution, we could look for that particular biosignature. So even though JWST can't go after biogenic oxygen, which is often held up as sort of the slam dunk biosignature, ground-based telescopes, the extremely large telescopes on the ground, will use a combination of direct imaging and high-resolution spectroscopy to look for oxygen in the atmospheres of these planets. So JWST will do CO2 and methane. The ground will do oxygen. And I'm also going to talk about recent work from my own group, again, that has looked at how can we be fooled on the ground looking at oxygen. Is it possible to discriminate between oxygen from a biosphere and oxygen from ocean loss? And we show that it is also possible due to the effect of oxygen collisions in a planetary atmosphere. When you have a lot of oxygen in the atmosphere, those collisions are present and they actually suppress the signature from the oxygen. So it turns out you actually can't see the false positive. So if you do detect oxygen at 1.27 microns from the ground, chances are that's the amount of oxygen you would expect from a biosphere. So I think, another thing that's very important to say at this time is that JWST and the ground-based telescopes will give us, at best, a tantalizing glimpse into the potential habitability and the potential for life on nearby planets. But to undertake the sort of comprehensive search we really need with large statistics and a comprehensive wavelength coverage and heightened sensitivity, we are going to need more capable telescopes in the future. And some of those are being considered for the current Astro 2020 Decadal Survey. And so I'll talk a little bit about those missions as well in my talk.
Great. Okay, thank you all. We will now open the floor for Q&A. If you have a question, please raise your hand. We'll bring you a mic and kindly state your name and affiliation before you ask a question. Okay, we've got one in the front row here. Thank you.
Clive Cookson from the Financial Times in London. I'm going to put each of you on the spot and ask you to give a percentage rating of the likelihood of confirmed extraterrestrial intelligence detection within the next decade. When I wrote a piece about what was going to happen in the 2020s in science, I said 20%, and most of the readers thought that was much too high. I'd like you not just to give a vague answer, I'd like you each to put a figure on it, please.
Well, I actually happen to think that anybody who gave you a figure would be talking about religion and not science, because that's a belief system, right? We won't know the answer until we know the answer. But we can tell you how much we are improving the phase space that we search for either technosignatures or biosignatures. And the supposition is that as you look at more places and frequencies and in different ways that you haven't looked before, the probability of success improves.
So I'm going to let X equal the probability of detection between 2011 and 2021. And I will say that the probability of detection confirmed between 2022 and 2032 is 1,000x.
Right. I agree with Jill. I am not going to give you a number for that. And I think that's because, you're sitting on our n=1 case here. We only know of one planet with life on it definitively. And I think that's something that's so exciting about this field is that we are really moving into the unknown, trying to determine whether or not there's any other sign of life elsewhere. But I will say that this idea of probabilities is definitely one that is a big thread through astrobiology at the moment. But that determination of probabilities is focused on our ability to assess whether something is due to life or not. And so there is a big push in our field at the moment to try and get things like the Rio scale for biosignatures to assess, I've seen this thing, great, I might think it's a biosignature, but how do I prove to the public that this is indeed far more likely to be due to life than to be due to planetary processes? And so that's kind of where the frontier is in my field at the moment.
But you notice we're all working on these problems. So it's pretty clear that we're optimistic.
Oh, yeah, here's the mic.
Andrew, does your answer mean that you think that the capacity over the next decade is 1,000 times greater than it was over the last decade?
Yeah, that's exactly what it means. Yeah, we've seen just a dramatic explosion in the number of observatories, the number of scientists, particularly the number of young scientists like Sophia that are working in this field, that are positioning themselves to dedicate their careers to it. And it really is a dramatic change from what we had in 2013, 2014.
And in the case of biosignatures, we simply have not had the capability to study terrestrial exoplanet atmospheres, but we will have that in the coming decade. And so the phase space now is wide open for that exploration.
Question here.
Hi, I'm Christina with the German news agency DPA, and I was wondering if I'm correct or if you might speak about there's two schools of scientists. Sort of one believes that it's better or to listen for signals, and other than it's better to send signals, and what might be the pros and cons of sort of those two strategies.
Let me start, and I'm sure Andrew has things to add, but if you're going to transmit, Christine, you have to start and never stop. Right? Because if you transmit for a finite amount of time, your message is going to go past your intended receiver in that amount of time. And if they don't happen to be looking at you in just the right way at just the right time, it won't be very successful. So you need, if you're going to be serious about this, you need to do it as a long-term project. On the other hand, we have been leaking, not deliberately transmitting, but we have been leaking radar and television signals for best part of a century now. And so we do have a bubble that's expanding beyond the Earth, a light year per year. Very weak because we didn't put a lot of gain in it for them. We were trying to illuminate the folks in the next county, right? But still perhaps detectable by a very advanced technology.
I think from a sort of scientific experiment design standpoint, it's very difficult to imagine how some relatively small scale or even large scale messaging to extraterrestrial intelligence project would somehow increase the probability of us being detected relative to the leakage that Jill mentioned. So I don't think that there's, in my view, there's not a lot of scientific utility in it. I think I'll sort of set aside some of the kind of controversial aspects of this, but I'll say that personally, I think imagining what we might say to an extraterrestrial civilization as a thought experiment is a beautiful kind of human thing. And I think from the perspective of philosophy or art, it's a wonderful question to ask.
Andrew, you said tomorrow you're going to reveal 2 new results from Breakthrough Listen. One is the first observation of a galactic plane, I think you said. What can you tell us about that? Elaborating more.
Yeah, so a fundamental principle, really, of the Breakthrough Listen initiative is openness and transparency, in particular with regard to our data. We spend our careers developing very intricate and sensitive algorithms to detect the kinds of signals that we think might be indicative of technology, but we're far from the only experts in the world at signal processing and signal detection, and we very much would like to engage the world in the task of looking through our data, trying to understand it, trying to look for new types of signals. And this, our second formal data release from Breakthrough Listen, doubles the amount of publicly available data that we've ever released. And as you mentioned, it includes observations of the galactic plane. So our first data release included largely observations of nearby stars. So if artificial transmitters are relatively weak and relatively numerous, then observations of nearby stars is a preferred strategy. But if artificial transmitters are relatively rare, but perhaps can be very, very powerful, then doing surveys of something like the galactic plane is a better strategy. And the data that are in question here come from the Parkes Observatory and their multi-beam receiver, their 13-beam Parkes multi-beam receiver. And there's something of order 500 terabytes of those data that are now available.
Question here?
Dan Falk, freelance science writer. Okay, I'll try to phrase this so that it's more likely to elicit a concrete answer than the question about probabilities, but it is related to that one, which is that when I'll say when rather than if, but either way, when a signal is eventually detected, and let's say it's unambiguously, from, not of a natural source, what is the probability that it will be intelligible to us? And I'm just, I'm imagining a press conference just like this one 30 years from now, where, the scientists tell us there's been a signal and it has the following statistical properties, and we don't know what it means. So any thoughts on that would be cool.
Well, for the past, since 50 plus years that we've been doing SETI, we've been doing radio searches and optical searches. But we're now starting to use more preferentially the term searches for technosignatures to indicate that we are as eager as Vicky is for these large ground-based telescopes and even more powerful space-based telescopes. And we're starting to think about what they might image that would be an unambiguous example of a technosignature. Perhaps my favorite example is this wonderful TRAPPIST-1 system that has 7 small planets orbiting a little M-dwarf star. They're all at different distances from the star, so they should all be at different temperatures and have different properties. But what if we make an image of that system and they all look the same? Perhaps they even all look like Earth's, right? That would be pretty unambiguous evidence of some pretty large-scale astroengineering. So the other thing that I would say is I could be happy with a cosmic dial tone as a signal, because in that dial tone, we learn something incredible. We learn that it's possible for us to have a long future. And that's a statistical result coming from the fact that if we are to succeed ever in SETI, then on average, the longevity of a technological civilization must be large. Not large compared to our timescales, but large on cosmic timescales. Otherwise, there'll never be 2 technologies that are close enough to one another to be detectable, but also cotemporal, lined up in the same time along this 10 billion year history of our galaxy. So that's a particularly spectacular piece of information. It's possible to have a long future. Somebody else made it through. We can do it too.
I'll just add that I think that being able to decode information in a signal, I think, is an incredibly hard problem. And we need only look at our efforts to understand animal communication here on this planet to see how hard a problem it is. And I think while decoding the signal is going to be very, very difficult, I think what Jill mentioned about the TRAPPIST system is interesting, because I think we might be able to understand something about the context of the signal, where exactly it's coming from, how it repeats, these kinds of things that might tell us something about ET, even if we don't actually decode information that might be contained in the signal.
Can I just add a comment there, not from Seti? I know you were asking probably about an intelligent signal, but even just in a signal from non-intelligent life, those things are going to be very difficult to interpret. And another thing in the field of astrobiology is looking at interpreting biosignatures in the context of their environment. And I'll just point out that, yes, we may get a biosignature, but we may not know how to interpret it either. And so that's another big sort of frontier in this field. And to be able to interpret that biosignature, you must understand the environmental context it's in, not just the planet, but how it interacts with its star and how the rest of the planetary system interacts with that planet. And so that has launched sort of this massively interdisciplinary effort to try and understand, how do we characterize the actual environment of the planet and understand that potential signature of life in that context. So yeah, interpretation is also a problem for us because it's not sending modulated radio signals. It's a much more cryptic message that's being sent to us by those microbes.
Question here. Comes the mic. Yeah.
On Goldsmith Interstellar Media. Follow up on that thought in a way. Suppose you had an unambiguously unnatural signal, which, yes, you'd have tremendous difficulty interpreting, except you would know it was unnatural and likely to come from an extraterrestrial civilization. What kind of plan does the scientific community, in particular the SETI community, have to deal with sending a response? That is to say, would it not galvanize all sorts of intriguing groups on Earth, starting with the religious, who would know exactly the direction, if nothing else, to start sending a reply message, never mind the time delay? And is there any hope of sort of gaining scientific attention as opposed to some other kind of attention for responding to the news that there was an extraterrestrial signal?
Well, the community at large that is actively working on SETI has for a long time now had an unenforceable consideration or decision that if a signal is detected, that no response will be made until there is some sort of global consensus about who will speak for Earth and what will they say. Now, it's totally, how do you get a global consensus? Right? It's totally unenforceable, but it is an example of our good intentions. Maybe that's the best we can do, because anyone really who has a large telescope and the budget to power it and transmit probably can and will. And I sometimes think of Freeman Dyson when we talk about this, because he has been saying for a long time, and wouldn't that absolute cacophony be about the best portrayal of current society on this planet today?
I think unavoidably it would attract all kinds of attention, scientific attention and otherwise. I'll point out, just to sort of echo what Jill said, astronomers aren't particularly well equipped to do transmitting. We have access to vast resources for listening, but really not that much for transmitting. So I don't think that the SETI astronomers that made such a discovery, be it of technologically capable life or of some basic form of life, would be the ones trying to talk back. I think it would be other communities.
Oh, here we have a question. Okay.
Muhammad Mansour from Egypt. Life, as we know, includes the presence of oxygen, methane, and other materials. If there is a probability that any life in any form at the universe doesn't include this material, if yes, will the new strategies will be useful to use?
Yes, so that is a very good question. So you're talking about sort of the different types of molecules that life can produce that we know that it can produce, so oxygen, methane. And so another frontier in the field of biosignatures at the moment is the so-called agnostic biosignatures. And so agnostic biosignatures do not assume a known metabolism which produces these known gases that we know about. And so an example of an agnostic biosignature would be understanding a planetary environment to sufficient complexity that we can understand that there is a disequilibrium in that atmosphere, that the molecules that are there would normally react with each other, and the fact that they still exist there means that there is an active flux of them from the surface. So the disequilibrium itself is not a biosignature, but it points to a flux that we then have to interpret. And the thing is, it doesn't have to be of a known type of gas. It simply has to be understanding the relationship that gas would normally be destroyed, but clearly there's a source of it, and then we have to try and interpret what's going on. Another example would be complexity of chemical networks in an atmosphere, and this is work that Sarah Walker's looking at ASU. And her group is looking at just the complexity of the networks, even with oxygen in there, that changes the way that chemical reactions occur in an atmosphere versus Venus and Mars. And so again, we're not presupposing any type of metabolism, we're just saying this is a very unusual pattern. So we're now looking at sort of trying to find patterns that are sufficiently unusual that they do not appear to be likely to be produced by planetary processes. So we are trying to push to life as we don't know it by looking for these anomalous patterns.
I think there's a kind of a technosignature analog to this agnostic biosignature approach that Vicky was talking about, which is that we're often asked, are you looking for TV transmissions? Are you looking for cell phones? What kind of technology are you actually looking for? What if the life is silicon-based instead of carbon-based? These kinds of things. And in SETI, particularly in electromagnetic SETI, optical SETI, and radio SETI, as we've been talking about, our searches are completely agnostic to the form of the life that's producing the signal, and even agnostic to the form of the technology that's actually producing the signal or the purpose for why it's being produced. We simply look for compression of electromagnetic energy in time or in frequency or some kind of modulation that is inconsistent with the astrophysical background or the instrumental background and consistent with something that technology could produce. So it doesn't matter if it's a laser communication system being used to communicate with a spacecraft in some exoplanet system, or it's a giant laser light show that some very advanced civilization produced for the amusement of all the life in their system. We would detect those things in equal measure with our experiments.
And there's one more thing, Andrew, that you didn't mention in terms of the things that we're on the threshold of. The ability to use machine learning to help us find signals in noise, I think, is really exciting. Historically, we've asked a machine to tell us if a particular pattern, frequency and time, could be found. But now we're on the brink of being able to say to the machine, are there any patterns in there? And so another type of agnosticism.
I think there's something particularly sort of romantic about the idea of machine learning and artificial intelligence looking for extraterrestrial intelligence, which itself might be artificially intelligent in some way.
Andrew, you mentioned a lot of interest from young people in the field, even more than there was in 2013 and 2014. Why is that? Are they drawn to the technological advances or some other feature of the work, I think?
Well, it's all of those things, and I think maybe I'll say one thing, and then I think Sophia should actually answer this and tell you, directly why she's interested in it. But I think there's an opportunity for a future career in the field, which I think there hasn't always been.
Great.
Yeah. Hello? There we go. So my personal path, I didn't intend to get involved in this research. It just happened to be an opportunity that came by. And I think that's a lot of the way that people are coming to it. Undergraduates now who are interested, graduate students who are doing this work. It's an interesting scientific problem. And there's now the technological resources to actually make inroads that we were not able to, say, 5 years ago. So there's a lot of low-hanging fruit, a lot of things to do. And there's also the resources to fund a career in it, hopefully. But at the very least, summer programs and things for students that didn't exist before. So there's a lot more available opportunities to get involved with this. And I think, as with anything in astrobiology, the work itself is just kind of inspiring and interesting in a way to astronomy students that it's always been interesting, but now there's actually opportunities to get involved that there weren't before.
Great, thanks.
And it also isn't so far out in the fringe anymore, now that we have exoplanets and extremophiles. So you don't have to fight that particular problem.
I think I saw it was maybe a piece, I don't remember if it was an editorial, but something in Nature talking about habitability and the use of that word to describe exoplanets. Is that something that you're concerned about, Victoria, in the way that you see coverage in the mass media, public perception?
Yeah, I think the coverage is concerning. I will say that the astrobiology community, those of us who use that term and understand what it means, we are fine with it. I think in the interests of sort of trying to inspire some controversy or something, people have attacked it. But we in the astrobiology community understand it to mean a planet that's capable of maintaining liquid water on its surface. And that is a criterion that we use for exoplanets in particular, because we want to be able to see a biosphere, which, if it's on the surface and interacting with its atmosphere, is much more accessible to our telescope. So it's really just a definition of a type of target and that we're looking for, but also this idea of the habitable zone, which people also can potentially go after. But the habitable zone itself is really, you can think of it as kind of a probability density function. It's a place where we think that life on the surface is more likely. It's not a benediction. It doesn't mean that if you find something in that zone that is in fact habitable. And so we in the field understand that, but I can see how there might be sort of potentially an opportunity for confusion with that. But I think it's just very important to make sure that that message is clear.
Question in the front.
It's Bill Diamond from the Seti Institute. Just a quick elaboration, actually, on what Vicky said, because on the one hand, there's this notion of the habitable zone and this probability density function. There's also the fact that while a habitable zone planet is no guarantee of a life-bearing planet, at the same time, we have candidates for life-bearing bodies in our own solar system that are scientifically outside the habitable zone, namely Enceladus and Europa. So on one hand, we have to be careful what we imply when we talk about the habitable zone. On the other hand, we shouldn't rule out systems or bodies outside the habitable zone for their potential for life.
But you can rule them out for our potential to detect life over 10 parsecs. And so that's why we have that definition. So within our solar system, we can send robotic spacecraft. And I will clarify, Andrew mentioned that I might be talking about in situ life tomorrow. I will not be. So I'm only going to talk about exoplanets. But for looking for life in situ, actually on the body itself with the robotic spacecraft, yeah, absolutely. We have a lot more environments we can get to because we can fly there and we can drill and we can do all sorts of things. Unfortunately, it's really hard to look for life across, parsecs of distance. And so we're trying to make it easier for ourselves by saying, okay, we're going to look at those planets where it's more likely that the ocean will be on the surface than maybe the biosphere is on the surface, and so we have a fighting chance. But trying to find out if there is life in the subsurface of a distant 10 parsecs Europa is just beyond us.
What kinds of robotic advances do you need in those spacecraft to do that work better? What kinds of craft improvements would you hope to see?
For in situ probing? You mean?
Yes.
Yeah, so within the solar system?
Yes.
Yeah, we have a number of missions that are going to, actually being in the system is important. So we have the Europa Clipper that's coming up that's going to look at that. But we're really... It's really quite hard to get below the surface of these objects. One potentially interesting object is Enceladus, where we have a plume that's venting out Europa has a little bit of that as well. And in fact, the discovery of the Europa Plumes with HST recently actually caused the people to go back and look at data taken by spacecraft again, and to realize that, oh, we actually do have evidence in previous data. And so that was kind of a synergy between the astronomy and the solar system community in being able to point that out. And so that has actually changed some of the programming of the Europa Clipper so that we can have a better look at what's venting from Europa, and to see whether that gives us some clues to the subsurface ocean.
Great. Well, if there aren't any other questions, thanks so much to our speakers. That was a fascinating briefing. We appreciate your time, and I wish everyone a great rest of the day here at AAAS. Thank you.